Yeah, we still have a couple of minutes before.
Yeah, okay, perfect.
Yeah.
Please announce our seminar as broad as possible. Invite friends, propose topics to discuss, propose talks. Thank you so much for your efforts. I really appreciate emails which I already got from you, from some of you. And well, the longer we survive, the better.
I've just received your email, Vladimir.
Yeah, thank you, Luca. Thank you. It's excellent. Yeah.
Okay. So do you think middle of May could work for a talk?
Yeah, absolutely.
Okay.
Absolutely.
Okay. Fine. Thanks.
Hello, everybody.
Hello, Lynn.
Hello.
Hello.
Okay, so let me welcome you again. And we have Mark Edelman with his talk about fractional dynamics. So Mark, go on, please.
Thank
Share
you.
the screen.
Thank you again, Dmitry, for organizing this series of seminars. So let me share my screen with you. And this is the topic of my talk, cycles in discrete fractional dynamics with power law memory. So why cycles? And you see, I just submitted summary of my proposal to NSF, and the reaction of directors was quite simple. So why do we have to study cycles? What is so important? Fractional dynamics, yeah, it existed for a long time, but why cycles? And again, it's a little bit different from what people most, in many cases in physics, investigate. It's diffusion and transport in general, where fractional derivatives appear, and in many cases spatial. But here we're talking about really dynamics as fractional evolution in time, which implies memory, and particular power law memory. So talking about regular nonlinear dynamics, it starts with calculating solutions, and solutions are fixed and periodic points. Or if we are talking about non-linear dynamics, it's also chaos in such systems. But everything begins with defining periodic points and the stabilities and period doubling cascade of bifurcations route to chaos. And even in chaotic systems, periodic points play quite important roles. They define the skeleton of chaotic attractors. And talking about fractional systems, it is known that there are no periodic solutions except for the fixed point. And people are trying to find some ways to analyze those systems. They again start looking for solutions, drawing bifurcation diagrams. but bifurcation diagrams actually depend on the number of iterations after which you get those diagrams. After 200, it looks awful. 5,000 iterations on each trajectory, it's a little bit better, but still quite uncertain. And to analyze stability, people introduce Lyapunov exponent, but it's a bit absurd because conversion is according to the power law, conversion of trajectories and diversion in chaotic case, in the unstable case. And those definitions, they are, in many cases, they are meaningless. So to start, we need to find periodic solutions. And this is not simple. So how to do this? And first of all, let me talk a little bit about the definition of discrete fractional systems. There are a couple of reasonable, I would say, really in the spirit of dynamics with memory definitions of fractional discrete systems. In principle, people introduce fractional, let's say, logistic map in different ways. Like Stanislavski did it. He used numerical algorithm to solve differential equations as a map. And again, you draw, he drawn bifurcation diagrams, more or less correct or not, and made some conclusions. And conclusions, they look like, in the fractional case, if there is memory, there is more stability or more chaos. And this is, again, not completely correct. And the other way to define fractional maps, as people did, like logistic map, you simply divide the general expression for logistic map by 1 plus ax squared, for example, and assume a equals to 0 of, oops, sorry, in the case of a regular map, and then when a is not 0, you have fractional map, and it's again, it's not in the spirit of fractional dynamics, as dynamics with memory. So the first significant breakthrough was done in the work by George Zaslavsky, with whom I worked a lot, and Vasily Tarasov. And they introduced fractional maps in the same way as regular universal map is introduced in regular dynamics. It's as a solution of the differential equations of a kicked system. And this is the equation. And in the regular case, alpha equals to 2. Yep. Now, if you substitute 2 for alpha, one is getting a system with really with memory in the spirit of fractional calculus. And this is the key element, memory, to define fractional universal map. Another key is kicks. But in this way, fractional universal map was introduced, and then fractional standard map, and the particular form was G is sine of X. But this allows introduction of fractional maps for alpha more than 1, because if alpha is less or equal than 1, then it leads to the equations that can be obtained solving these differential equations. They include the value of function g at the time of kicks, when alpha is more or equal than 1. And at the time of kick g is undefined. Okay, I mean x is undefined and correspondingly g is undefined. So in order to extend this definition to be able, for example, to consider logistic map and to introduce universal map for all alpha more than 0 or even equal to 0, you need to introduce some small time delay, infinitely small. Then the system can be solved, and it requires standard initial conditions for the fractional differential equations. And then I will consider only case of Caputo derivative. And initial conditions are different for Riemann-Liouville and Caputo fractional derivatives that can be used. Why Caputo? Because in this particular presentation, I will consider alpha between 0 and 1, and Riemann-Liouville maps for this case are identical 0, because in many cases, in most cases, identical 0, because it requires initial condition at x0, and in order to have solutions of this equation, which are not divergent at time 0, it requires 0 initial condition. Momentum can be not 0, but initial x, it's from the structure of solutions, and from the fact that here initial condition is for the negative derivative, actually, at x equal to 0. Okay, I will not go in more details, but I consider fractional Caputo map, and this is the universal map. Those are terms which depend on initial conditions. This is the function, force of those kicks, and the memory is power law memory. H is period of kicks. That's it. Now, this is it was the first way to introduce fractional maps. The other one is comes from fractional difference calculus. So as there is regular calculus, there is there exists also fractional difference calculus, so continuous or difference calculus, where instead of integral operators, I used sums, and instead of derivatives, finite differences of any order, and in regular case, it's integer order. And definition, the most consistent definition and introduction of fractional integrals and derivatives used on generalizations or generalization of Cauchy formula for the n-fold integral. And the same generalization exists for the n-fold sum, and this is how fractional sums can be introduced. So you consider n-fold sum, defined it as in the following way, and it can be reduced to just simple sum, but with this kernel. Again, it's almost power law. Here, those parentheses, the meaning of those parentheses is a falling factorial. And falling factorial is defined by the next formula, by this formula. And what is important here is that it is asymptotically still power law. For large arguments, it's power of the argument. Okay. Now, similar, not similar, just exactly identical result for the n-fold, for the alpha, let's say, or n integer order or alpha order sum was obtained by Miller and Ross back in 1989, and they used Green's function approach. And they derived the same formula, which is true for any alpha. And then Anastasio in 2009 introduced Caputo fractional difference. And again, in the spirit of the same definition for the in continuous calculus as a fractional sum from regular m's order of fractional, no, not regular, forward difference operator. This is the forward, sorry, it's here. This is a standard definition of forward difference operator. Mm-hmm. So now we have discrete fractional calculus, and the thing is that now the solution of a simplest fractional difference equation can be written as a fractional difference map. So we have universal fractional maps, a solution of a system of with kicks, with periodic kicks, and now we have also a fractional difference map as a solution of a fractional difference equation. This is a Caputo map. Those are initial conditions. And again, the difference between previous and this case, fractional and fractional difference is this. It's falling factorial. Okay. And again, we can consider this map for integer values of alpha, and they, as in fractional case, they give volume preserving maps for all cases except alpha equals to 1. Now, in a similar way, fractional difference of H maps can be introduced. It's here you consider not difference operator, but H difference operator, which is extension of delta X over delta H, not just delta X. And when you have this equation with extension of this operator for any delta H, you then may obtain, this map. And definitely when H goes to 0, you obtain fractional, differential equation, not difference equation. And those are corresponding definition. This is falling factorial, but this is H falling factorial that appears in those equations. Okay, so we have two kinds of maps. And they both can be written in the following form. Now, what is interesting is that definitely not only those two definitions, but majority of different definitions fall into this class of formula. So x, a new value of x is a convolution from all previous values. And in most cases, it's this function is asymptotically power law. It shouldn't be exactly power law. It should be asymptotically power law. So the systems that we will consider, for which we will try to find periodic solutions, are of this kind, convolution. And they include also fractional, Riemann-Liouville, Caputo, all, even though I don't consider here Riemann-Liouville. And if I consider alpha between 0 and 1, it will, in most cases, give 0. Exactly 0 will appear if this function g of 0 is 0. And it's true for logistic map, and it's true for standard map, for sign map, for circle map. Okay. Now, in relation to the introduced fractional and fractional difference map, G is this G tilde is defined in the following way. And for fractional maps, this G, sorry, U for fractional maps is n to the power alpha minus 1. And for fractional difference, it's defined through gamma functions and falling factorial. Okay. Now, a small deviation from smooth continuation of this talk, I'll just introduce some particular features that are fundamentally different from the solution of equations with no memory. And oops, come on, okay. Somehow I cannot move my, okay, I moved it. So this is the thing. Again, there are no periodic solutions for fractional maps, but there are asymptotically periodic solutions. And here on two graphs, we have on the top, it's we consider fractional maps, and on the top it's fractional difference, and it's a particular form of the map with G, which defines logistic map. And in both cases, systems, it is shown that systems have, for those values of parameters, and alpha is 0.1, and K is different in both cases, but the solutions, asymptotically periodic points, are of period 2. So if we wait for a very long time, then finally there will be those solutions which are written here for the top, and similar result is different a little bit for fractional difference. But and again, if we are talking about logistic map, you know that it's defined for x between 0 and 1. And you see, for significant range of initial conditions, on the first case, it's up to 0.6. The solution behaves like that. It goes like this, and then like this, and then it breaks. No, what it means? It means that a system with which fixed point is unstable, which, and in both cases, okay, systems with unstable fixed point, they start the evolution converging according to the power law. If it were a stable fixed point, system converges its solution to the unstable fixed point. Fixed point is unstable, but there is power law conversion to this point, and it may continue for millions of iterations, like here. Yep. And then system suddenly breaks and start converging to the periodic point. And here it's shown that conversion is really as power law to the fixed point. For example, here it's the case of unstable fixed point, unstable period 2 point, and system first converges to this unstable fixed point, but then at certain point after almost 100,000 iterations, it breaks. Okay, so this is a fundamental feature of those systems with power law memory. Now, talking about cycles, we assume now that this convolution equation, it's this one, yep, that it has periodic points. Okay. Then those for large values of n, those solutions should converge to some periodic values. And in finding this total, we want to separate terms with different values of m. Terms with converge to different values. So there will be totally here L different values of xk to which solution converges. And again, I want to mention that this series U alpha is divergent because it behaves at asymptotically as n to the power 1 minus alpha, and alpha between 0 and 1. So series is divergent without G. Now, with G, we want to rearrange the whole total in parts. So first we start with the first term, we add second up to L. Then next term is L plus 1, L plus 2, and so on. And this is the last row. But now we add terms in columns. And this is a rewritten expression with L different totals. And now, to analyze this series, we consider differences because U alpha is a divergent series, but the differences are now convergent because they have power alpha minus 2. And this allows to consider in this total, in those totals. Now, again, we have L totals here, L minus 1 and additional 1. We may, we will have convergent series and we will try to factor out values of G. So let's assume existence of those limits and consider n goes to 0, and now we may rearrange definitely a sequence of summation in infinite case because we have absolutely convergent series U alpha. And all results are based on a couple of theorems which are proven in that paper that I mentioned. It's already, it should appear online in nonlinear dynamics because I submitted proofs, they said 4 days ago. And a week after submitting proofs, it appears online. So it will, this paper will appear, but a couple of theorems which intuitively seems okay, but they are strictly proven using this alpha, epsilon n or epsilon delta formalism in that paper. So if we have a sequence AK, which converges to A, and a series which is absolutely conversion, then the total sum, it's convolution, this convolution, is convergent to, is equal to AS, this limit. This is one theorem, and I will show approximately how it can be proven. And the second one is that if S is infinite, then the only way in which sigma is finite is when A is equal to 0. Okay. And this is the basis for the proof. And again, oops. We go to the next slide. And there are L totals in the definition of difference x of two consecutive values of x. And it can be written like that. And we separate this total, split this total into two. One up to n1, and then from n1 to n. And we can see the limit when both n1 goes to infinity and n minus n1 goes to infinity. Let's see. Here we have differences. It's a convolution, so it's n minus maximum here would be n1. So this difference can be quite significant, and the difference of g from its limiting value will be very small. It can be made smaller than any number, and then it will allow to factor out g from the first total, and the second total goes to 0 as remnant of this series goes to 0. Actually, how to pick up two values of n, and L and D, such that if that when n1 more than nl and n minus nl more than nd, the difference between those sums and those values can be made less than epsilon for any epsilon. And those values of sums are defined by the following series for any s. Okay. It just power law, or it's asymptotically power law. So finally, those equations that define differences can be written in the following form. Okay, so we have L minus 1 independent differences. So we have L minus 1 equations that define L periodic points. We need one more equation to close the system. And as they look very simple, those S that they are defined only by the type of derivatives and definition of fractional difference that we use. They're the same for any maps, those S. And the G actually defines the map. Now, to close the system, we consider also total of all periodic points. And here, all terms except for this one are finite. And here we will use this second theorem, which requires a total of all G must be equal to 0. This is the only condition on which that middle row on previous page would be a finite value. And again, we simply split total into two totals. And again, the exact proof is in that paper. So now we have L equations which define L periodic points. Now, the simple matter is to solve it. There are some technical difficulties in calculating those series because they converge very slowly, like this. And numerically, for those, there are plenty of papers which appear where people analyze different systems or the same systems by different methods. And they don't find, they're not finding periodic points. And here it's just algorithm for those people to use to calculate. And I gave tables and formulas in that paper for practical calculations. To calculate that total of like this, but to infinity, you select first some finite value of n, which can be like 20,000, 100,000, and for PC still, it will be less than a second to calculate that total. And then the remaining total, in the remaining, you may factor out 3k to the power with a large k to the power alpha minus 1, and then consider Taylor expansion of the difference. And then it can be shown that formulas can be expressed in the following form, which contain, oops, let me, I have difficulties with my cursor. Oh, okay. I can move. Okay. Now, those formulas which contain a Riemann zeta function. So there are some finite totals and the Riemann zeta function, and there are plenty of algorithms one can find for fast calculations of Riemann zeta function. This is for fractional maps, those formulas, and for fractional difference, again, there are some asymptotic formulas for calculation of those terms in the expression for those sums S, and finally, again, this is example of S2 that can be calculated using Riemann zeta function. Okay. Now here, those S, they are not independent. Total of all S should be 0 from S1 to SL, those coefficients. And here I explicitly calculated, so whoever wants to to solve equations for L equals 3 cycle, those values of sums, and to check the validity of those calculations, I also calculated totals, which are very close to 0, the last column in both. Tables for fractional and fractional difference map. This is the same for period 2. Now, there are two particular forms that can be investigated that were already well investigated when G is K sine X. We have fractional standard map for this. Actually, we may call it fractional circle map or fractional sign map, because for L equals to 0, it gives sign map for alpha 0. For alpha 1, it gives circle map. For alpha equals 2, it's standard map. It's one family of maps. And a logistic map, which gives the actual logistic map in the case of alpha equals to 1, is defined by this value of function G. And those two equations which define periodic points, period 2, let's say, they can be written in the following form. And in this case, it can be solved and the limiting value can be found. And Kc depends on the value of S. Yep. And now on those equations can be solved using function S, and critical points at which a transition from stable fixed point to period 2 points, here they're depicted on two-dimensional alpha K diagram, bifurcation diagram. So for fractional difference map, here there is stable fixed point and above stable period 2 point. And again, it's up to a certain point where period 2 point becomes unstable and so on. And previously reported results were obtained by direct calculations of map, multiple simulations, and then they were obtained by direct numerical calculations, second consecutive bifurcation, and so on. But those graphs are exactly coincide with previously reported results. And this is for fractional difference, and the upper curve for it's actually transition from, it's bifurcation curve from fixed point to period 2 for fractional maps. Okay. Now, here I've drawn a few return maps for fractional difference logistic map. So for in the first case, in all cases, alpha 0.75, and the first case corresponds to stable period 2 solution, and those stars, they are calculated using my formulas that I derived. And this is fixed point, and there are here results obtained over 500,000 iterations. So there are 500,000 points, but you see that quite fast conversion to the fixed to period 2 points occur. And again, because maps are with memory, return maps are not just a single curve, xn plus 1 as a function of xn, as in the regular case. Now, those points, they are not on the same simple curve. Then the next Poincaré plot is for period 4 point, and again, there is clear convergence to period 4 point, and those unstable period 2 and fixed points, they're acting as a repeller. And the last graph is a chaotic area. Again, here there are unstable period 3 points marked with pluses, like this, and then another period 3 point. And we have period 2 unstable point and repeller actually, and fixed point repelling, but the diagram looks like chaotic attractor. And here is a zoom of some of the port, which shows quasi-fractal structure of this Poincaré plot. So now we have instruments to investigate regular motion solutions of difference map, asymptotic behavior of regular maps and chaotic maps. Now, those are examples of bifurcation diagrams for fractional systems. And here alpha 0.3 cases, fractional and fractional difference standard maps for alpha 0.8, 0.3 for very small alpha, but they look like regular bifurcation diagrams. It's for standard map. Here bifurcation diagrams for logistic map, and they again look like regular bifurcation diagrams. Now, this is the property of regular bifurcation diagrams. If we consider those transition period doubling bifurcations, then at this point, for example, fixed point becomes unstable, and solution of corresponding equation become unstable, and period 2 solutions become stable. So there is a bifurcation in corresponding equations. Here, 2 extra solutions in equations appear, which for smaller values of k were complex solutions. Now they become real solutions. So it's kind of bifurcation points, and then next bifurcation points, and so on. And in the regular dynamics, it's known, it was shown by Feigenbaum, and he got Wolf's Prize for this, that there is a limit, this limit. Now, he obtained this result analyzing some kind of similarity and looking at properties of return maps. But now it's difficult to do anything with return maps. We simply have this kind of equations. And now, because we have the same bifurcations, we must have the same properties of solutions of those equations. So let's say we have this equation for large, for t or 2 to the power n cycle, and depending on k, on a parameter of a map, there should be corresponding transition in, bifurcations in solutions of those maps. Points where there is a transition from complex solutions to real solutions, and this analysis should be now performed on those equations. And it's interesting that it should be the same independently on actually not independently, but on very wide class of function of G. We must have the same properties, and they should somehow be extracted from the structure of those equations. And this is actually a program that I proposed as a on an SF and some other proposals, but I still don't know how to do it, and I have to persuade people to do it, so that this problem is really interesting. Okay, and this is the conclusion. I used exactly 50 minutes, but conclusion is based on all my previous statements that now we have instruments to investigate regular and chaotic behavior and of fractional systems, and this instrument actually should be used, and there are plenty of pure mathematical problems here. And I finished. Oops. I am ready to answer questions if there are any.
Thank you so much, Mark.
You are welcome. So I stop sharing. And by the way, Yuri, you remember I told you that that you got this power law conversions you demonstrated on one of your slides in fractional systems. And again, here I have power law conversions, but of trajectories and power law diversions, but I can verify it numerically. I don't have proofs.
Okay, thank you so much. Vasilius.
Hello, it was a really nice talk. I would like to ask if the Poincaré maps have the same behavior if the step is random or if the power of the kick in a kicked rotor is random.
Well, this is a bit different situation. I mean, this is already a fractional system, and you have to you're asking about introduction of randomness into this random. I don't know. I actually, yep.
I have worked with random strengthening the kicks in my graduate thesis. That's why I'm asking if it's any different from random time kicks, because I had the quite similar results when it comes to topology of the trajectories. And I want to know if these two are interchangeable, the power from each kick in the rotor and the timing of each kick, if we can make those two interchangeable.
It's interesting. I'm not familiar with this result. I'd be glad to look to think about it if you send me a reference.
Yes, I will speak with Mrs. Meletlidou, and then we'll contact you.
But talking about introduction of randomness into systems with power law memory, with fractional systems, I actually have a model of the evolution of systems with memory.
Yeah.
And I showed you that what I modeled is a lifespan of living species. And if I again share with you screen, let's say.
Yeah.
Thank you very much.
You're welcome. So there are here. Let me go back to those graphs. Okay. Okay. Here, on for example, on this graph, it's system with memory, and this is how it evolves. Yeah? Again, there is Buffon for lifespans of living species. There is Buffon rules that time of development is 1/6-1/7 of the lifespan of living species, which is approximately the same for all those evolutions. But the thing is that those graphs, they differ by initial conditions. But if we are considering evolution of living species, then we may assume near zero initial condition, and it can be shown that there is then maximal lifespan, okay? Maximal time of evolution when X initial condition near zero, after which a system breaks. But now you may introduce, and if we are modeling a lifespan of living species, then we should introduce some random mutations, whatsoever, random perturbations to this. And I showed that under those random perturbations, whether they are distributed normally or uniformly, in both cases, we are getting Gompert's law for the lifespans of living species, which is the real distribution of lifespans of living species. So this is the only case when I consider randomness on the top of fractional of memory. But I'd be glad to see your papers.
Thank you very much, Mark. Any other questions?
I would like to ask a question. The periodic solutions in fractional maps, they are asymptotic solutions, as you said.
No, there are no non-asymptotic. There are no
periodic solutions.
No, except fixed point.
Except fixed point, because there is a term that is limiting process.
No, you see, you may write those expression convolution for first three terms, let's say, and you see that there is no solution. They're inconsistent for first three iterations, and you'll see that there can be no periodic solution, and there is the strict proof of this fact.
But you take asymptotic periodic solutions because there is a limiting process.
Yeah. It's shown that asymptotically periodic solution exists, and I actually find those asymptotically periodic solution, and this algorithm that presented, it's to find asymptotically periodic solutions. And now analyzing those equations which define those, we may consider those bifurcation points, but it could be quite complicated, mathematically complicated problem.
Thank you, Mark. I think, well, it seems to me that, in fact, fractionality, in many respects, has a destructive effect on many properties of complex systems, and whatever we observed so far. Before we had nice pictures. Now,
some people say not. For example, in if it is you see, talking about bifurcation diagrams for, let's say, fractional standard and logistic map. When we consider fractional, bifurcation diagrams actually expand.
Mhm.
They expand in such a way that when alpha is 0, we have okay, no, but they expand. This is the fact.
Mhm.
They expand, and for fractional difference they contract. Now expansion, it means that system becomes for the same values of k, it becomes more stable.
Mhm.
Before, for example, transition bifurcation occurs at k equals to 3 for logistic map. Now it occurs for 3.5, 4, 5, and so on. So it becomes, in a sense, more stable. And more than that, even if it is unstable, it behaves for quite a long time as a stable. It converges according to power laws. It should be to this unstable fixed point. So it's just different.
I see. I see. Thank you so much. Thank you, Mark, for this excellent talk. Actually, I was really enjoyed, and I learned much from it. So, dear colleagues, thank you so much. Mark, please send me the slides so I could upload them and send out to all participants.
Okay.
And I hope next time we have a German colleague. I don't remember his name and title, but I will announce it in a while. Well, so if you have other talks, other guests, or other participants who might be interested to join us to make a talk, you're welcome. Please send me their emails so I could include them into our mailing list. Well, thank you so much and have a nice weekend. Stay safe and healthy.
Yeah,
Thank you.
we
Thank
try.
you.
Thanks.
Thank you.
Thank
Yeah.
you.
Ciao
Bye.
to all. Ciao.
All the
Bye-bye.
best. Bye.
Bye.
All the best.
Bye.